Good afternoon all. I beg to stand on the existing protocol. Our topic says strength properties of concrete made from different water sources by Cordelia, Nnennaya, Nnaji, and Nwonu. Concrete is a composite construction material made up of water, cement, aggregates, and sometimes extra materials called admixtures. Generally, concrete finds its use in virtually all civil engineering works. Concrete is the most widely used material in the world next to water. Water serves the following purposes. Number 1, to wet the surface of aggregates to develop adhesion, because the cement paste adheres quickly and satisfactorily to the wet surface of the aggregate than to a dry surface. 2, to prepare a plastic mixture of the various ingredients and to impart workability to concrete to facilitate placing in the desired position. 3, water is also needed for the hydration of cementing materials to set and harden during the period of curing. The quality of water in the mix plays a vital role on the strength of the concrete. Water approved for drinking is generally satisfactory for usage in concrete production, but there are exceptional cases. For instance, in some arid areas where local drinking water is saline and may contain an excessive amount of chlorides, undesirable amount of alkali carbonates and bicarbonates, which could contribute to the alkali-silica reaction. However, some water that is not for drinking may be fitted or suitable for concrete production. The aim of this work is to compare the compressive strength of concrete mixed with different sources and qualities of water. The research was concentrated on sources of water from Nsukka environs. The sources are rain, river, and potable water. At each of the water locations, a 25 liters gallon was used to collect water samples. These samples were taken to a water analysis laboratory, and the physicochemical compositions of these water qualities were analyzed and ascertained using standard methods. The coarse aggregate used was granite with an average size of 20 mm. The fine aggregate was river sand. The cement was ordinary Portland cement. Particle size distribution of aggregates was performed according to BS 8121 1975 at the Civil Engineering Laboratory, University of Nigeria, Nsukka. SLUMP test was carried out using the SLUMP tool. Aggregate impact value was done using aggregate impact value machine. Moisture content was ascertained with moisture content apparatus, and finally the compressive strength test was carried out. The total quantity of materials used in the concrete production were 23.22 kg of cement, 11.61 kg of water, 46.44 kg of fine aggregate, and 92.88 kg of coarse aggregate to produce concrete mix of 1:2:4. The batching was done by weighing. The mixing of concrete was done manually at a water-cement ratio of 3.5. Concrete cubes production were carried out in accordance with BS 1881 Part 108 1983 using cubical molds of size 15 by 15 by 15 cm. This concrete was poured into the mold and tampered properly so as not to have any voids. Each layer of concrete receives 25 strokes of a 25 mm square steel rammer. The top surfaces of these specimens were made even and smooth by putting cement paste and spreading smoothly on whole area of specimen. After 24 hours, these molds were removed and test specimen immersed in water for curing. These specimens were tested by compression testing machine after 7, 14, and 28 days curing. Loads were applied gradually at the rate of 140 kg per cm cube per minute till the specimens failed. Load at the failure divided by area of specimen gave the compressive strength of concrete. Tests on specimen were carried out in duplicate and average values taken. Table 1 shows the physicochemical parameters of water samples. Figure 1 shows the graph of sieve analysis of fine aggregates. Sieve analysis results: fineness modulus of sand as a fine aggregate. Fineness modulus is an index number which represents the mean size of the particles in sand. It is calculated by performing sieve analysis with standard sieves. The cumulative percentage retained on each sieve added and divided by 100 gives the value of fine aggregate. From figure 1, the finest modulus for the fine aggregate is 2.46, implying a zone 2 fine sand of particle size ranging between 2.36 and 4.75 mm. Table 2 shows the properties of concrete tools made from different sources of water. Figure 2 shows average compressive strength test of concrete tools made with different water sources. Discussion on SLUMP test results. Table 2 shows result for SLUMP test. It can be seen that concrete made with potable water had a SLUMP value of 20 mm, which indicates a true slump and signifies low workability. This means that when unsupported, concrete after lifting mold slumps uniformly all around. The area of top surface of mold is equal to top surface of unsupported concrete after slump. Due to this very low workability, this concrete is suitable in road making and roads vibrated by power-operated machines. Concrete made with rainwater had a slump value of 120 mm, which indicates a shear slump, signifying high workability. This means that one half of unsupported concrete, that's frostrum of cone, will slide down along inclined plane. If shear slump continues, the concrete can be described as having a harsh mix, that is, mix that shows lack of cohesion. This concrete is suitable for sections with congested reinforcement. It is not normally suitable for vibration. Concrete made with river water had a slump value of 240 mm, which indicates a collapsed slump, signifying very high workability. Aggregate impact value results. Table 2 also shows the aggregate impact value test. The value obtained from aggregate impact value AIV test conducted was 25%, and AIV of 25% falls into the category of classification as satisfactory for road surfacing and wearing costs. This value of the AIV can give us a level of assurance that when used in concrete production during execution of construction activities, the aggregate is capable of resisting and withstanding sudden harsh condition of exposure, as well as possessing adequate toughness property, that is, the property of a material to resist impact. Total moisture content test results. Table 2 also shows the total moisture content test. The value obtained from the total moisture content test carried out was 0.39%. This implies that the amount of moisture, that's water, contained in the fine aggregate was about 0.39%, implying an air-dry AD fine aggregate. That is, all moisture are removed from surface, but internal pores are partially full. The AD represents the variable moisture content that will exist in stockpile aggregates. Figure 2 shows the result of average compressive strength test. The average compressive strength for concrete made with potable water increased with age, which are 16.67 Newton per mm square, 18.22 Newton per mm square, 20.22 Newton per mm square, corresponding to strength at 7 days, 14 days, and 28 days respectively. This implies that the 7-day strength is less than the 14-day strength, and also the 14-day strength is less than the 28-day strength, signifying that the strength increased or appreciated with age, and the maximum strength was achieved on the 28th day. This gradual increase in strength indicates that base concrete is reliable, durable, and has long-term strength on structures made by heat. The average compressive strength for concrete made with river water increased with age: 10.89 Newton per meter squared, 12.89 Newton per meter squared, 21.11 21.11 Newton per meter squared, corresponding to strength at 7 days, 14 days, and 28 days respectively. This implies that the 7-day strength is less than the 14-day strength, and also the 14-day strength is less than the 28-day strength, signifying that the strength increased or appreciated with age, and the maximum strength was achieved on the 28th day. It is to be noted that even though the compressive strength of concrete made with river water increased with age as that of potable water, in the case of river water, the increment was very sharp after the 14th day. This concrete can also be reliable, durable, and also has long-term strength on concrete or structures made by heat. The average compressive strength for concrete made with rainwater increased with age at 7 days, that is 20.45 Newton per meter squared, and 14 days, that is 22.11 22.11 Newton per meter squared, but there was a sharp drastic reduction in strength on the 28th day. That is 13.56 Newton per meter squared. That is, strength at 28 days is far less than that of 7 days and 14 days. This implies that the 7-day strength is less than the 14-day strength, and also the 28-day strength is less than the 7-day and 14-day strength, signifying that the strength increase are appreciated with age, and the maximum strength was achieved on the 14th day. This indicates that this concrete cannot be reliable to show durability and long-term strength on structures made by it. Conclusion: potable water has more favorable physicochemical properties, as can be seen in Table 1. It was observed that the concrete produced with potable water and river water had their compressive strength gradually increased with age, while the concrete produced with rainwater gradually increased too, but later decreased in strength at 28-day age. The results indicated that sources of water used in mixing concrete have a significant impact on the compressive strength of the resulting concrete. It concluded by suggesting that potable water is the best water type for concrete production, since the concrete cubes obtained from it gain appreciable strength with age. River water could be used for mixing where potable water is scarce. Recommendation: this work has the following recommendations. Potable or fresh water should always be employed in the production of concrete to enable it to attain maximum compressive strength over time. All water intended to be used for production of concrete must be evaluated to make sure it conforms to the laid down standards. Strict adherence should be given to specifications, most especially in any issue concerning reinforced concrete structure. Water without obvious concrete-inimical substances should be used in concrete batching. Thank you for listening.